Alright, so let's have some more fun with ice tables, KPs, and some other things that hopefully you haven't forgotten. So carbon tetrachloride is a common, well, it used to be a fairly common solvent. It's a bit carcinogenic, so we kind of don't want to use it that much anymore. Um, so again, it's a carbon with just 4 chlorines on it. It is at 700 Kelvin degrees for sure. I mean, it's a liquid with a relatively high vapor pressure, room temperature and pressure. If you heat it up to 700 degrees Kelvin, 700 kelvins, sorry, it decomposes into graphite, solid carbon, and chlorine gas. So this is a long problem. It's going to take a couple slides, so make sure you've got a few sheets of paper to take notes. Buckle up and know that this is about as complicated as one's going to get. So if you can follow along and do one like this one, you will be fine. So I'm taking 2 moles of pure carbon tetrachloride, and I'm putting it into an evacuated 10-liter container. Again, so evacuated just means that there's nothing else in there. And more importantly, no carbon, no chlorine, just carbon tet. And it's in a 10 liters, so 2 moles, 10 liters, we know what the concentration is. Now, and you also know that once equilibrium has been achieved, that there's only 1.4 moles of carbon tetrachloride that remains. We have 2 questions. 1, what's Kp for this reaction? And then 2, let's fire up a different container here with carbon tet and see what's going to heat it up and see what the partial pressures of carbon tetrachloride and of chlorine are going to be once equilibrium is reached. So part A is like one of the earlier examples that we did. Part B is a little more complicated, and it's more like the phosphorus pentachloride example that we just did just a few slides ago. So let's get going. All right, let's do this. All right, so let's get our ice table going. We've got the reaction written here. And so we've got initial, we've got equilibrium, of course change in the middle. This is going to be a Kp, so these are all going to be pressures in atmospheres. Start with what you know and what you don't need to calculate. So you know that there are 0 atmospheres of chlorine initially because you were told that you started with just pure carbon tetrachloride. And also, since carbon is a solid, it's not going to have a partial pressure, so we can just ignore it. I should add at this point that KPs usually only have gaseous components in them. All right, now we have to calculate stuff. So I told you the initial and equilibrium amounts of carbon tetrachloride, but not the pressures. But with the handy-dandy ideal gas law, we can figure this out. The partial pressure of the carbon tetrachloride, let's say initially, is going to be equal to its initial amount times RT divided by V, and we know all these quantities. So I just got to plug them in. So initially we had 2 moles, and that is going to give us 11.48 atmospheres of carbon tetrachloride initially. So we will put that there. And the other thing that I told you was the equilibrium amount of it. And so we're going to calculate the equilibrium pressure exactly the same way. We had 1.4 moles, and if you plug in the rest of this, that corresponds to a equilibrium pressure of 8.04 atmospheres. And I'll put that there. Note, I kept an extra sig fig here just to minimize surrounding error. And so that's basically all you can do with the information that I gave you initially, but you can still do quite a bit. So now, with these 2, we can figure out what the change was. So it's going to be 11.48 minus 8.04. So that's going to be a drop of 0.345 atmospheres. And now that we know that, we can use the reaction stoichiometry to determine what the change in the chlorine was. So they react 1 to 2. So we can say that the chlorine must have went up 0.69, so that's just twice 3.45. And that gives us a equilibrium pressure of 6.9 atmospheres of chlorine. And now we have everything we need to calculate the Kp for this system, namely this pressure and this pressure. just going to plug it in. So it's going to be the partial pressure of chlorine squared divided by the partial pressure of the carbon tet, and that gives us 5.92, and we will need to remember that number for the second half of the problem coming up next. And now that we've got the Kp for the system, we can attack the second part of the problem, which is a different setup. And here we're saying that we have 1.5 moles of carbon tet. We've got a smaller 4-liter container now. It's still at 700 Kelvin. And what's going to be the pressure of Cl2 at equilibrium, and well, just for yucks, the carbon mass. So what's different here in this case is we're given initial amounts, not the equilibrium amounts, but we can still do the same idea of building an ice table. It's just going to be algebraically symbolic to begin with. So let's do it. All right, got the same system. It's going to be Kp, so we're going to be working in pressures and atmospheres. Start with what you know and you don't have to calculate with, namely that the initial pressure of the chlorine is going to be 0 because we don't have any at all. And we can ignore the solid carbon. Now, you are given the initial amount of carbon tet, just the amount, not the pressure. You can use the ideal gas law just like we did in the previous problem, so I'm just going to give you the answer. In this case, it's 21.54 atmospheres. And so where do we go from here? Well, so that's all the information you're given initially. Now, since you have no chlorine to begin with, you can assume some reaction in the forward direction to make some, which means you're going to lose some of the carbon tetrachloride, which means at equilibrium you will have 21.54 minus X atmospheres of carbon tetrachloride. Now, if you look at the reaction stoichiometry, if you lose X atmospheres of carbon tet, you will make twice as much chlorine. So that pressure change is going to be plus 2x, which will mean 2x atmospheres. And from here on in, it's algebra from now, the chemistry is done. So let's just get through it. All right, so the Kp is equal to the partial pressure of chlorine divided by the partial pressure of carbon tetrachloride squared divided by the partial pressure of carbon tetrachloride. And this is equal to 2x squared minus, or divided by 21.54x, and it's equal to 5.92. I cannot stress enough the importance of getting this right. This is a very common algebra goof. So if you expand that out, you get 4x squared. So I know a lot of people, a very common mistake is they'll have this as 2x squared because they will square the x and not the 2. Don't make that mistake. And it's going to be equal to 127.5 minus 5.92x. So that's just cross multiplying these two right here. And to get that in a form to where you can apply the quadratic equation, that's going to be 4x squared plus 5.92x minus 127.5 equals 0. And ignore that. All right, so again, we're going to use our quadratic equation. Again, x equals negative b plus or minus b squared minus 4ac, all divided by 2a. Plug in the right numbers here, and I will leave you to do this. Practice. You will have a quadratic equation needing equilibrium problem on the exam, so I may as well practice it. And you'll get two roots, 4.95 and negative 6.43. Now in this case, we can discount the negative 6, so one root makes sense, the other one won't. We can discount the 6.43 because that would give us a negative pressure for the chlorine, which we don't want. And so the 4.95 gives us a positive and also gives us a positive pressure of carbon tetrachloride. So that is the root we are going to use. And we can now that we know what x is, get these values up here. So this means we've got, at equilibrium, we will have 16.6 atmospheres of carbon tetrachloride, and we will have 9.9 atmospheres of the chlorine gas. And again, check. So 9.9 atmospheres squared divided by 16.6 atmospheres does in fact give us 5.91, which was the stated equilibrium constant, so there's a good chance that our math is right. Woohoo! And we are finished with this problem. Pat yourself on the back if you got through it.